Effects of large-scale oceanic phenomena on non-cholera vibriosis incidence in the United States. Implications for climate change. At the beginning of the article, they introduce the bacteria of genus Vibrio, found in North and South America, Asia, Europe, and Australia. This bacteria is the main focus of the research article. The bacteria causes cholera and non-cholera vibriosis, or NCV. The infection is transmitted through food or exposure to contaminated salt water. In 1988, the CDC established the Cholera and Other Vibriosis Illness Surveillance, or COVID system. The infection shows an increase of cases in the summertime, but more importantly has shown a significant increase in national NCV cases over the past decades. The El Niño Southern Oscillation, or ENSO, is an irregular and periodic weather trend, and extreme weather events have been associated with NCV outbreaks. This article combines environmental exposure with national case counts to evaluate the variation in vibriosis risk. In the introduction, they focus on 13 references. References 1 to 4 focused on where cholera and NCV are found and how you can be infected, the reported rates of cases of cholera and NCV in the United States. References 5 to 9 were more about the symptoms of the pathogen, the mortality of the infection, and how ocean warming affected other infections. References 10 to 13 concentrated on ENSO and the potential impact of extreme weather events on NCV outbreaks. Pathogens of NCV are thermophilic, and climate change could increase the risk of an NCV infection because of this. They hypothesized that the annual risk of infection increases while latitude increases. The relative rate of increase in this risk, due to climate change, would be greater at northern latitudes rather than southern latitudes. This trend is particularly stronger in coastal states, as ocean warming is one of the main effects of climate change. Methodology. So the data used was obtained from the United States Center for Disease Control Prevention. From this data, case counts by state were extracted manually from published maps. To ensure accuracy of extractions, monthly case counts were summed and compared to nationally reported case counts. When necessary, missing years were estimated using linear extrapolation and interpolation. The environmental data used was based on ENSO, which is a complex climatic phenomenon manifested by changes in sea surface temperature and atmospheric pressure. They used the National Oceanic and Atmospheric Administration's Multivariable ENSO Index, or MEI, which is used to monitor ENSO activity. The data from the index was obtained monthly from January 1999 to December 2014. This MEI data was used for the western states, while the North Atlantic Oscillation Index, or NAO, which was also obtained from the NOAA, was used for the East Coast. While the effects were felt widespread, they were mainly felt in the western states. National analyses were evaluated year on year, including seasonal trends and overall case using count-based regression models. They then constructed negative binomial models from this. Census population estimates were used as model offsets. These initial estimates were made by monthly MEI and NAO index values, which were mentioned previously. These values were then generated into a trend model with 12-month periods. After this, they were able to construct a nonlinear model to evaluate the integrated effects of environmental exposure over multiple periods. They first created one model for MEI and NAO, and then these two models were both later combined, and this final model, which you can see on the left, has a cubic polynomial relationship. The regional analyses evaluated relative incidence by using negative binomial models once again. They also evaluated linear trend terms for each region separately, and the associations between vibriosis risk and the annual mean MEI and NAO index values. To either confirm or deny their hypothesis, they had to evaluate if the trend exhibited a north-south gradient that suggested a connection to climate change. To do this, they constructed a meta-regressive model using the latitude of state centers as a variable. Overall, there was a total of 10,862 cases of vibriosis from 1999 to 2014. 99% of these cases could be assigned to a specific state. During this 15-year time period, the national rate of infection increased threefold. This is about 0.11 cases per 100,000 population in 1999 to 0.336 cases per 100,000 population in 2014. This total increase works out to be about a 7% increase in rate every year. There was a trend of seasonal oscillation during the period studied. This was because of a rise in cases predominantly during the summer. There was a significant increase in risk in the non-Pacific regions. The highest increase of the incidence risk was in the Atlantic and behind it the non-coastal regions. This is because these regions had the lowest baseline for infection rates. Even though the Atlantic regions experienced high increases, the risk of infection for the Pacific and Gulf regions was still the highest overall. ENSO had the most significant effect on the incident rate compared to NAO, which showed an insignificant amount of influence over the incident rate. Meta-regression models of the incident rate ratio of each state showed that increasing latitude showed an increase in the risk of infection. However, there was no significant difference in the interaction between latitude and coastal or non-coastal states. Toxigenic via cholerae is an extensively studied bacteria, but this is believed to be the first study relating increases in incident rate to climate change. The sensitivity of vibriosis risk related to ENSO suggests climate change is likely to drive further increase in risk in the near future. In the US, the vibriosis risk is expected to double in the next year, all due to ENSO. The increase in risk will be the greatest at northernmost latitudes, where vibriosis has been historically less common. This work suggests that vibriosis may be an important sentinel for the impacts to come of climate change on infectious diseases. Overall, the authors believe that these models present a model that can be applied to other infectious diseases. So, in conclusion, the authors found 2 lines of evidence suggesting that climate change is an important driver of observed increases in risk. One of these is the north-south gradient trend, with a relevant increase in infection as the latitude increases. The second is that vibriosis risk was strongly associated with ENSO-like oceanic changes. Attributing these 2 trends to climate change and ocean warming is biologically plausible and is inconsistent with studies done in different locations around the world.